Hi, this is my video number 5 for mth3101 advanced calculus. Alright. In the previous video, I talked on the line integral where I just give the example of a open arc. Yeah, it's not a closed curve. Now, let's say example of if you have a closed curve. Closed curve. For example, I'll give you an example for the particularly for the closed curve, because next is that we are going to deal with the Green theorem where the line of integral is a closed curve. All right. So let's say example of this. Let's say we want to evaluate this integral, given the c 2xy minus xy dx plus x plus y squared dy, where c is given as y equal to x squared and x equal to y squared from 0, 0 to 1, 1 to 1, 1 and back to 0, 0. Let's say I want to evaluate this integral. Alright, so if you look at C here, so we have plot this a little bit. We sketch that yx squared, and if you look at the limit of integration given here, the limit given here is just a positive, so we may consider just one part only. We have let's say this is your y equal to x squared, and for y, x equal to y squared is we have that. Okay, just take this side. This is x equal to y squared. So if you look at this our curve here, so from 0, 0 to 1, 1, that, and from 0, 1, 1 to 0, 0 we have this. So this is we consider as a closed curve. Closed curve. It means begin from one point and end up to the same point. So that's we consider as a closed curve. So in this case, we have two piecewise smooth curve. That's considered this as a C1. That's considered as a C2. Okay. So in order to evaluate this, to evaluate that or to perform the line integral, this is what we are looking for. C, all right, with whatever integrand there. This is equal to, we split this into, for each of those smooth curve. So we have C1, plus C2. Because in this case, our C is C1, C2. Now, we consider each of these one by one. First consider C1. So our C1, y is equal to x squared. Y equal to x squared. And we parameterize this equation, make it the system of parametric equation. Then you can let x equal to t, y equal to t squared. Okay, I don't want to make you confused. Of course, we can just from here you just substitute y with x squared and then differentiate dy. You got 2x dx and just substitute into that. Yes, you can, but we stick into the what we have done earlier, that we give a parameter, we form a system of parametric equation. Alright, then from there we can substitute into the main problem that given. Now if you let x equal to t and y equal to t squared, so we can find what dx is. This is equal to dt, and you can also have dy, which is 2t dt. Now since we take x equal to t for the limit of integration, since we take x equal to t, so then we consider the point for x, x as a moving point from 0 to 1. So our x is from 0 to 1. So therefore, since t is x equal to t, so we can also take t from 0 to 1. I hope you can get that. Then now you can start the integral, those t, along C1. Along C1, you can write everything there. 2xy minus x squared dx plus x plus y squared dy. Taking into account all those substitution we need, then substitute into there. So what we have here, this is integrate our C1 now, t from 0 to 1, t from 0 to 1, 2x squared, we have 2, our x is t, our y is t squared, minus x squared is t squared, our dx is dt, and we have plus, our x is t, y squared, y is t squared, so plus t4. Alright, and dy is 2t dt. 2t dt. Again, if you what we have done, that we have changed from two variable integrand here, we have x and y. Now we change to a single parameter t, integral that involve only t. So now you can evaluate this easily. So what you have, I think I just want to give you the solution here. Alright, can I? This is 0 to 1. So we have this one is 2t cube. We don't have 2 cube, so we have 2t cube here, 2t cube minus t squared here. Okay, minus 2 squared. So we have 2t squared there. So that one minus, that one plus 2. So we have plus t squared. And we have here plus 2t to the 5th. Alright, then this is dt. Okay, so you evaluate this, that give you 7 over 6. And then we need to consider C2. Having done that, we need to consider C2. Okay, let me stress again, you can do this by just differentiate, substitute y into x squared into this, and then differentiate dy, that give you 2x dx, then substitute again into that without using this. You can, but again, I don't want you to get confused, because this is what we have done in the previous video. So I'll stick to this, and it's nothing wrong. Okay, now let's consider the other path, C2. For C2, what we have, our C2 is x equal to y squared, x equal to y squared. Now in this case, we let y equal to t, not x but y. Y equal to t. That gives us x equal to t squared. The reason why, if we choose x equal to t, it's not wrong, but you have to write y in terms of square root t later on. So we don't want that. If possible, we don't want to have a I would say a weird function. I mean, it's not nice function. We want it a very nice function. Okay, so that's why we have those. We choose that kind of substitution. So then we have this thing, and then for the limit of integration, we look at this y equal to t. Then we look at limit for y. Y is from, this is 1, 1, 2. So we have one. Look at y here. Y 1 to 0. So our y is 1 to 0. Alright. So therefore our t also from 1 to 0. So therefore the integral, our integral along C2 for 2xy minus x squared dx plus x plus y squared dy. Okay, so that gives you, well, we have integrate t from 1 to 0. Okay, from not from small to big, but from where to where. So now from 1 to 0. So 1 to 0. Now we have 2x squared, 2x. We have 2x. Our x is t squared. Our y is t times t minus x squared. We have t4. Then we have dx. Dx is dx. From here, this is 2t dt. So 2t dt plus, again x, we have t squared plus y squared is t squared. Correct? Yep. And dy is dt. Okay, simplify this. We have 0 to 1. So what we have, t2 cube. We don't have 2 cube there. So here another 2. So we have 4 t cube minus 2t4 plus 2t squared dt. Okay, so evaluate this. You got minus 17 over 4. Alright, so therefore I need a little bit more space. Therefore integrate C, integrate C, this is C1 plus C2, that give you 7 over 6 plus minus 17 over 5. Yeah, so that give you 1 over 30. So that's your final answer. This one is minus 17 over 5 here. It's not that clear. Okay, minus 17 over 5. So this is the example of the closed curve. Yeah, closed curve, and the curve contain piecewise smooth curve. So this one smooth here and this one smooth here. It's not whole curve is smooth. All right. Now, having done this thing, especially that involve the closed curve, I would like to continue our lecture with the our next theorem that we call green theorem. Yeah, green theorem. So what the green theorem says, let P of xy and Q of xy are two functions, you see, two function which have a continuous partial derivative. continuous partial derivative. In the region D, D is a region. Continuous partial derivative means if you differentiate p with respect to x, respect to y, as well as we differentiate q with respect to x, with respect to y separately, those are still continuous. It means, so px, py is continuous, qx, qy continuous. So that means they are continuous partial derivative. So in D and C is a simple closed curve, and C is a simple closed curve. I have defined what is a simple closed curve. So completely in D, then if we integrate along C, p dx plus q dy, this is just the same as we integrate over the region R, where R bounded by C, del q del x minus del p del y dx dy. Where R is a region bounded by C. Okay, for the proof of this theorem, of course we have a proof. I don't want to prove in this class. Instead, I would advise you to look at the any calculus book basically. You can find what is the green theorem, and you can find the proof there. It's not the proof is not difficult to follow, and as well as you can search in the internet, of course. Yeah, there is a proof for the green theorem. It's not difficult. So let's see. Let me describe this thing. Look at the example, the previous example, right? This is the previous example that we dealt with. Okay, we have a closed curve here. Yeah, this is closed curve. This is one of the example. You can try this. Then we can use the green theorem in this case. Yeah. So if you use the green theorem, see what happened. I hope it's work. As long as C as a simple closed curve, so we can apply this. So you can see from here, if you use a line integral, you have to consider C1, you have to consider C2, and so on and so forth. But if you use the green theorem, so let's see this example. We want to solve this same problem C, 2xy minus x squared dx plus x plus y squared dy with C is given as y equal to x squared and x equal to y squared using green theorem. Okay, first identify that as a p as a q. Yeah, p dx, not q dx. Yeah, p dx, q dy. So remember that one. So p, our p is 2xy minus x squared, and our q is x plus y squared. Now for q, we differentiate respect to x, so we have del q del x that give us 1. Okay, whereas for p we differentiate with respect to y, so we have del p del y that give us 2x, right? 2x. What about the limit of integration? I'll explain to you a bit later. Now, first thing, how to transform that from line integral into the region integral. Yeah. So just consider that. So we have our r del q del x minus del p del y dx dy, that give us integrate. Then del x del q del x, that's 1. Del p del y, this is 2x. Now we can differentiate this with respect to y first or x first. Now look at this region. Okay, if you consider we want to differentiate on with respect to y first, so which means we want to take y first here and then end up with x, so which means we have dy dx. Now we look at the region of the limit of integration for both x and y. See, look at the sketch here. So we know that this is 1. This is 1. Okay, so x from 0 to 1. So this is x from 0 to 1. This is x-axis. Now for y, we take the small function as a lower limit and bigger function, or bigger function for the upper limit. So in this case, no, bigger and smaller function with respect to which axis that we are looking for. Okay, so in this case, the axis that we deal with as a x-axis, so the bigger the small function, the bigger the smaller function depend on x-axis. So if you look at here, the area for this is smaller than the area for that. So I would say this is a bigger function, and this is the smaller function, this is the bigger function. So for that we have y from x squared. Okay, so we have y from x squared to this function c2 here. This function, you can write y as a surd of x, positive, because this is the positive part. The negative part is this one, so we don't take into account the negative, so that's why we just consider positive. So which means y from x squared to surd x. Alright, and x from 0 to 1. X from 0 to 1. So this is much easier for you to solve. Alright, and I think I don't have to do this for you, or should I? 0 to 1. So we have the integrate respect to y. So we have y minus 2 xy, y from x squared to surd x dx. That give you integrate x 0 to 1. Those who have surd x minus 2x surd x, so 2x 3 over 2. Alright, then this one minus x squared minus 2x cubed dx. Then you can solve this. Yeah, you can solve this. This will give you 1 over 30. Try it. So if you compare these two methods, definitely for the line integral, you need to consider each of those curves separately and then solve each of them, right? And then whereas for the green function, you only have to evaluate once, then give you the result straight away. So if by looking at these two approach here, definitely the green theorem will make our life much easier. Alright, but you have to consider the condition that in order to use the green theorem, you must have a closed curve, and must be in the counterclockwise direction. Yeah, counterclockwise direction. All right. So that's the example of the green theorem. So let me give you another example. I have a couple of examples actually to share with you. Okay, let's say you want to solve, give you another example. You want to solve this integral c 5xy dx plus x cubed dy, and this circle here means c is a closed curve. Yeah, c is a closed curve, so we therefore can use the green theorem. Alright, and c bounded by yx squared and y equal to 2x. So first thing is that it's not compulsory to sketch those curves, but with those curves, if you do sketching, then it will help you a lot in determining the limit of integration. Yeah. So let's sketch those things. So we have 2yx squared and y equal to 2x. This is easy to plot. So we have y equal to x squared. So let's say we have y squared. This is that y equal to x squared. I just consider the positive part, the negative part this side, so I just ignore because we just need the positive part. And y equal to x squared, so we have, let's say this is just a straight line passing through 0, 0. This is y equal to 2x. So this is our region R, and this is our C. You can use again the line integral, where consider each of these one by one, C1 and C2, or you can use the region itself, region bounded by curve C. So those regions are bounded by C, where our C is C1, C2. Now we can use the green theorem in this case. Yeah. So our P is 5xy, and for P we differentiate to respect to y. Yeah. So we have here, this is 5x, and we have for Q we have x cubed. For Q we differentiate that with respect to x. That gives you 3x squared. Okay. Then we substitute everything into the those formulas. So we have those integral becomes over R. Okay. Del Q del x, we have 3x squared minus del P del y, that's 5x. And then we differentiate. I think we can consider that on x axis again. So therefore we differentiate, integrate respect to y, then the x. Now for the limit of integration, you need to solve this equation to find what is the point of intersection there. So we have y equal to x squared, 2y, so we have x squared equal to 2x. Right? Do not cancel out. Minus 2x, that equal to 0. Yeah. Do not do this. Yeah, don't do this. X squared equal to 2x. You cancel that, then x equal to 2. You lose 1 point. Yeah, this is wrong. So what you need to do is this. You factor out that x minus 2x. So sorry, x minus 2 equal to 2. So you have x equal 0 and 2. See, here you only have x equal to 2, but here you have 2 point of x 0 and 2. So therefore the limit of integration for x 0 to 2, so this is equal to x from 0 to 2. Remember that the most outer integral must be a constant to constant, some numbers to some numbers, not a function. Whereas for y, look at the smaller function and the bigger function. This is smaller function as compared to that, so y x squared to the other one is 2x. Then put everything there, so we have 3x squared minus 5x dy dx. Then you can solve this. That's integrate from x 0 to 2. This one integrate respect to y, so we have 3x squared minus 5x y, your y from x squared to 2x dx. Alright, so I can do this because the integrand doesn't involve any y, so we have a constant respect to y. So here you have x equal to 0 to 2. Then just substitute everything, so we have 3x squared minus 5x. That one we have 2x minus x squared dx. Okay. Then you can simplify all those things. So the final answer you got is at minus 28 over 15. Okay, so let's consider two more example. Let's say we want to evaluate C to xy dx plus x squared plus y squared dy, where our C is ellipse 4x squared plus 9y squared equal to 36. Okay, of course in this case I think you can write in terms of that we have x over 3 squared plus y over 4 squared is equal to 6 squared. So which means you have on the x-axis, on the y-axis, this is 3, this is 3, and then this is 2, this is 2, so this is your ellipse. That's your ellipse. Okay, then if you use the Green theorem, we have our P is 2xy. P we differentiate respect to y, that gives us 2x. For Q we have x squared plus y squared. For Q we differentiate respect to x, that gives you 2x. So if you substitute those things, integrate over r, where your r is here, that's your r. Okay, so integrate those, and del q minus del p, we have del q del x minus del p del y, the dy dx, that give you, we integrate over r, del q is 2x minus del p, this is again 2x dy dx, that you got 0, then everything give you 0. Okay, now can you think of this thing? I'll try to change so that this will not give you 0 with the same same curve. Alright, so let's say I leave this part as an exercise to you. We integrate over C, where we have, let's say this is we have 2xy dx plus, I don't want to give to have a 0 here, so probably we can have I don't know, see what happened. Just let's say 2x squared plus 2y squared dy. Okay, so that you not got 0 here, where our C is same curve, 4x squared plus 9y squared equal to 36. Try this as an exercise. Alright, if you don't try, then I put in the exam. That's good. I give you one more example. Let's say we want to evaluate C with we have 4 plus e to the third x dx plus, here we have sine y plus 3x squared dy, where our C the region, or the, I wonder how to write this thing. This is our C. Okay, that's a C, and this is A, this is B. So basically in the first quarter, this is our R. So our R is bounded by C, a quarter of the annulus. Yeah, a quarter of the annulus. Right. Okay, so C, where C is a quarter of annulus of radius, or radii A and B. First quarter, I would say. First quarter of annulus of radius, radii A and B. Okay, and then again from there you can use the Green theorem, because this is closed curve. We use the Green theorem. We integrate over R. Okay, integrate over R. Del Q del X, you got 6x. Yeah, don't worry about those sine x and square root, also difficult. No, don't worry about those things. And then this is P, you differentiate respect to y, that gives you 0. See? So now it's easy. This is d dy dx. Remember that this is a circle, or a quarter of circle, then you can use a polar coordinates. Okay, use polar coordinates. Circle, use polar coordinate. So in this case we integrate our R from A to B. Yeah, our R from A to B. Then our theta from, this is a quarter, so 0 to pi over 2. So theta 0 to pi over 2. Then our x, 6 is just a constant. I can take out 6. Our x is equal to r cos theta. Yeah, x is r cos theta. And dx dy is r dr d theta. Okay, so this is for x. Remember that for the polar coordinate, we have x equal to r cos theta, y equal to r sin theta, and dx dr equal to r dr d theta. This is dx dy. Yeah, where r in this case is the Jacobian of the transformation. So having done this, so it's easy for you. I just give the solution then. This give you 2b cubed minus a cubed. That's all. Yeah, because this is a very strict integration, so I don't have to go in detail on those things. All right. Okay, so with that example of Green theorem that we use, we apply the polar coordinates, and as well as in the example here, I suppose maybe you can also use the polar coordinate, because our but you need to write this in terms of circle. You transform into a circle, use polar coordinates, and then you can solve this problem much easier. Okay, so with that, I stop here for this video. Then we'll meet in other video. Bye for now.